This integral is probably too hard for Calc 1 or Calc 2, but it's not so bad if you know a thing or two about the complex numbers. The techniques we'll use were discovered in the early 1800s by the French mathematician Augustin Cauchy. The Cauchy integral formulas describe the relationship among the outputs of certain complex functions when their inputs come from either 1, the interior of a closed curve, or 2, the curve itself. Moreover, the first derivative, second derivative, on up each obey a similar formula relating their outputs on the closed curve to their outputs inside the closed curve. Let's look at the complex version of this integral over the closed curve C. C has two pieces, the interval from minus r to r, and that semicircle part we'll denote by CR. We can split the integral over the entire curve C into two integrals, one along the semicircular part and the other along the interval from minus r to r. Something amazing that you're about to see is that the integral has the same value no matter how big the radius of the semicircle actually is. This is because of the Cauchy integral formulas. Notice that point I is always within the semicircle. Also notice that you can factor the denominator, and z minus I cubed is a factor. Let's take the remaining 1 over z plus I cubed and rename it f of z. Now we can apply the generalized Cauchy integral formula. The third power of z minus I in the integral corresponds to evaluating the second derivative of our function f at I. And thus we've shown that the value of the integral over the semicircle of radius r is 3 pi over 8. Now I made a mistake here saying the same value for all r. I really want to make sure that I is within the semicircle, so r should be any number that's bigger than 1. As we let the radius of the semicircle grow, we've shown the value of the integral over the whole semicircle is 3 pi over 8. Let's restrict our attention to the integral over just the arc part. The absolute value of the integral over the arc is at most the maximum of the absolute value of the function you're integrating times the length of the arc. The length of the semicircle is pi times r, and I've used the reverse triangle inequality to replace any dependence on the value of the function just by the expression here involving the radius of the arc. But notice there are many more r's in the denominator, so this gets really small as r gets big. Therefore, the magnitude of the integral over the arc becomes negligible as the radius increases. So 3 pi over 8 must be the limit as we integrate along the bottom of the expanding semicircle. Thus 3 pi over 8 is the value of the real integral that we started with.